Welcome Pure Maths 1 students to week 8 of our maintenance series. Today we're looking at quadratics, functions, coordinate geometry, we're chucking in circular measure for the first time, and a little bit of differentiation. Alright, let's get into it. Well, the first one here, we have to find a set of values for k, for which the line y equals kx minus 4 intersects the curve, so this is quadratic, y equals x squared minus 2x at two distinct points. So remember, we're looking for a scenario where we've got something like this, or this, but not something like this, or something like, something like this, where we just touch at one point. Okay, that's a pretty terrible drawing, sorry about that. Okay, so that's the general idea of what we're trying to achieve. Let's see how we can do it. Oh, no, I'll have to rub this out somehow. Okay, there we go. Now, well, why don't we find out where the line, which is kx minus 4, meets the curve by making them equal to each other. Then we could bring everything across to the same side and make it equal to 0. Another way of writing this is, and this is very familiar to me. I wonder if we've done this in earlier weeks. Plus x, and I could factorize that x out like this. Okay, so I've just factorized the x out of these two here. Okay. Now, at this point, we will use the discriminant. And for there to be two distinct crossing points, there has to be two roots, which means that the discriminant has to be greater than 0. Okay, well, b squared is, b is made up of minus 2 minus k, so we've got to square that, minus 4 times a, which is the coefficient there, which is 1, and times c, which is the 4, and that should be greater than 0. So let's just expand this out. We get 4 plus 4k plus k squared minus 16 should be greater than 0. Let's gather everything together. We've got k squared plus 4k minus 12 is greater than 0. I'm going to factorize that to find the roots, or the places where it crosses the x-axis. A positive 6 minus 2. So if we were to sketch our graph, we've got a root at minus 6 and another one at 2. Something like that. And we want where it's greater than 0, and clearly you can see, I hope, that we've got a point here and a point here. Okay, so to define those, we've got x is less than minus 6, or x is greater than 2. And there we go, that's our quadratics question for the day. Moving on to functions. We've got a function that's made up of different parts depending on where we are with our domain. So the domain is between minus 1 and 4, but from minus 1 to 1 we use this top function here, and then from 1 to 4 we use this function here. Okay, well, let's just look at what the values are when we chuck in a minus 1. This is 3 times minus 1 is minus 3, minus 2 is minus 5. And you can see that this is a linear equation, right? 3x minus 2. That means that it's got a positive gradient, so it goes from minus 5, and we can find out what it's going to be at positive 1. So 3 times 1 is 3, minus 2 is 1. So it goes from minus 5 to 1. Okay? And you can kind of see that here, right? I presume this is this graph here. That's what we've got, right? That's that bit there. Okay, and then we move to a different function now. So we chuck in this 1 again. 4 over 5 minus 1, which is 4 over 4, which is 1. Which is good because it should be. Otherwise it wouldn't be a function because they are all meant one. At 1 you should only have one value. Otherwise it would be a one-to-many, which isn't a function. Okay, now we put in a 4 here. 4 over 5 minus 4, which is 4 over 1. So it goes from 1 to 4. So now we can state the range. What is the range? Well, the range is, we would write it like this. Minus 5 is less than or equal to fx. That's when you're talking about range, you want to write in fx. Is less than or equal to, and our highest value is 4. Now we're going to sketch the inverse function. Now remember with the inverse function, it's actually a mirror images because you're swapping your x and y values. So there's a mirror image across the line y equals x. So you're going to get some sort of shape like I've really done this pretty badly, but you're going to get some sort of shape like this, and then it's going to go out like this. Okay, so vaguely, I mean it's pretty badly drawn, but you get the general idea. Okie dokie, now we're going to obtain expressions to define the function, the inverse function. Okay, well let's start with this bit here. So we go y equals 3x minus 2. We swap our y and x values because we are doing an inverse. Move everything across so that we can get y by itself. So we get y is equal to x plus 2 over 3. Now, write that as in the inverse. Well, no, I'll come to that at the end actually. Now let's do the second one. Different color. I'm doing this bit here. So we've got y is equal to 4 over 5 minus x. I'm going to multiply both. First of all, I'm going to swap my y and x values over because that's what an inverse is. You're swapping your range and your domain. Then I'm going to multiply both sides by this 5 minus y. And then come up here. I'll divide by x. I get 5 minus y equals 4 over x. Then the last step is y is equal to 5 minus 4 over x. Right, so we've got our two equations, but they're not in function form or function notation yet. We're just going to do one more thing. We also need to give the set of values for which each expression is valid. Okay, in other words, we're giving the domain. Okay, now remember, if we want the domain of the function of the inverse, it's equal to range of function. Okay, that's pretty badly written. Okay, so all we need to do for each part is give the ranges that I've already worked out up here. So that was quite handy really. So we might go, we'll kind of write it a little bit like they have. We'll go the inverse function, and we've got two parts to it. So we'll have the first one, which is where is it? X plus 2 over 3, and that's 4 minus 5 is less than or equal to x is less than or equal to 1. And then the next one is, what is the next one? 5 minus 4 over x. Oh, that's a bit small. And that is for 1 is less than or equal to x is less than or equal to 4. And we're away and laughing. Done. Sorted. Now we're moving on to coordinate geometry. I might just move this down a wee bit so we've got some room. The midpoint of the line segment joining P and Q is M. Okay, well, and then point R has coordinates of -3, -7, show that RM is perpendicular to PQ. Okay, let's find the gradient of PQ. Because something's perpendicular, to prove it, we show that they are negative reciprocal of each other, or they multiply to make -1. Okay, so the gradient of PQ is equal to, I'm going to do 5 minus 1 over -4 minus 6 equals 4 over -10, which is -2/5. Now I'm going to do midpoint of PQ, which is where M is. So we add them together, we add the x's together and divide by 2, and then we add the y's together and divide by 2, and we get 1,3. So that's the midpoint. Alrighty then. At this point, we want to find the gradient of RM. Now we know where R is, that's this information here, so it's going to be, let's do y's, changing y's, 3 minus -7, so, and then we're going to go this one here, right, 1 minus -3, so this gives us 10 over 4, which is equal to 5 over 2. Now, how do we know whether these are perpendicular? Well, let's go -2 over 5 multiplied by 5 over 2 equals -1. Therefore, perpendicular. Okay, I'd probably write therefore RM is perpendicular to PQ. Something like that. Okay, that's jolly messy. Okay, so we're on to the circular measure question. We've got this diagram here, OAB, OCD, the radii of a circle with a centre O, so there's our centre there. We know that one's got a radius of 10, so that's this bit here. The other one's got one of 16, which is this bit here. And then we've got the arcs AC. And this is another arc. Okay. We know that alpha, that's the angle, is 0.8, so find the area of the shaded region. Well, the area of the shaded region is going to be equal to the area of the large the large sector minus the small sector. So the large sector is, remember your formula is half r squared theta for area of a sector. So we're going to go half times, now the radius of the large sector is this, and then theta in this case is 0.8. Then we're going to, so that would give us that whole area there. Okay. Now I want to take away, and I'll half times 10, so that squared times 0.8, and what I'm taking away here is that there. Okay, that's what I'm trying to do. Alright, now what does that equal? Well, we chucked that into our calculator, and I think when I did it I got 62.423 significant figures. Now I'm going to do the second one, which is find the value of A for which the perimeter of the shaded region is 28.9. Well, first step is to realize that this bit here and this bit here are each 16 take away 10, so 2 times 6 for those bits. Now that we've got that, oh, why is this not working? Now we want to find BC. Okay, oh sorry, BD. Now BD is going to be R theta. So r theta is the length of a is an arc length. Okay, so it's going to be for that one 16 times alpha, because we don't know alpha in this case, plus, and then the AC, this bit here, is going to be the r 10 times alpha. So we can simplify that to 12 plus 16 alpha plus 10 alpha, and we're told that this is equal to 28.9. So therefore 26 alpha, and I'll bring the 12 across to the other side. So we're subtracting, so that's what is it, 16.9, and then we divide 16.9 by 26, which is 16.9 divided by 26. This is giving me 0.65. Okay, there we go. Moving on to our differentiation question. We've got to find the equation of the normal to the curve at point 0, 1. Okay, let's say you've got a curve that looks something like this, and this is 0, 1, just say for an argument's sake. The normal will be going at perpendicular to that gradient. So what we're going to do is we're going to find the gradient at this point here by finding dy dx. Then we're going to do the negative reciprocal of it. Okay, so dy dx gives us our gradient, and we look at this, we go 3 times 3 is 9, 9x, drop the power down to 2. Then we go to the next one, 2 times 1, so it's 2x, drop the power down to the power of 1, so we can just leave it as 2x. Then minus 4x becomes minus 4, and the 1 drops out. Then we can find the gradient. The gradient at 0, 1 equals negative 4. Now, why do I know that? Well, you insert the 0 value for x, right? So the gradient at 0 is minus 4. Therefore, the gradient of the normal, and normal is perpendicular, isn't it? So it will be the negative reciprocal, so it will be 1/4. Now, to find the equation of the line, I'm going to use y minus y1 equals m into x minus x1. What's y? y1? Well, it's the coordinate. We know that that coordinate is on the normal, and we know the equation, the gradient is 1/4, and then x1 is 0, so it's like that. And let's just go over here. Y equals 1/4 x plus 1, and that would be our final answer. Well, I hope this is making sense to you all. Feel free to leave a question in the comments, or chat to me on ThinkWave, and I'll help you out if I can. Alright guys, good luck, see ya.